Hello children, now let's proceed further in that chapter. We were doing solution chapter. I have finished with the first small section of solution. Now moving on to the next section of solution, that is solubility of a gas in a liquid. Now I don't have to tell you the definition of solubility, you people know it, you have learned it in lower classes what is solubility, but here our syllabus or the curriculum only tells us to discuss about the factors on which the solubility of a gas depends. That is why the next topic, now you know that how much gas will be soluble, more gas will be soluble in a liquid or less gas will be soluble. This is what is given by solubility of a gas in a liquid. So what are the factors which determines? So here we are discussing the factors which determine the solubility of gas in a liquid. Now there are altogether 3 factors, but rather than 3 factors, I'll make that one single factor only into 2 factors. So that means there will be altogether 4 factors we'll discuss. So the first factor on which the solubility of a gas in a liquid depends is the nature of the gas. Now what is the nature of the gases? You know that some gases are more soluble in a particular liquid, then other gases may be less soluble. Now let us discuss about one solvent, the most common solvent, water. Now if you are talking about water, so if the solvent is water, okay, here it is. If the solvent is water, then there are some gases which are highly soluble in water, whereas other gases are there which are very less soluble in water. So it's less soluble, we can call it as sparingly soluble in water. So if I discuss here about sparingly soluble, less soluble and highly soluble. Yeah, by the way, I am here discussing only with respect to water. You know, maybe the solubility will be different for different solvent, but with respect to one particular solvent, water, there are some gases which are very little only they are soluble. For example, you know, oxygen is very little only it is soluble in water, sparingly soluble in water. Similarly, nitrogen, hydrogen, you know, these gases are very little only they are soluble in water. That's why we say they are sparingly soluble in water. But at the same time, there are also gases like carbon dioxide. You know, carbon dioxide is highly soluble in water, especially under pressure. Now we'll see that's one of the 4th factor. There we'll discuss about that pressure also. But carbon dioxide is more soluble in water than oxygen. So highly soluble in water. But then again, 2 more gases I think which you have know it in detail. In fact, you have learned about them in class 10. 2 of them. One is HCl, hydrogen chloride gas, and the other one is ammonia. I think you people will remember this solubility of these 2 gases we have also demonstrated with the help of an experiment, that fountain experiment. So here a red fountain was formed in ammonia, blue fountain was formed. So you know that actually depicts, that actually tells us that these gases are very highly soluble in water. That is why the first factor that we are discussing is about nature of the gas. So how the gas here, if the nature of the gas is such that if like gases like oxygen, nitrogen and hydrogen, less only they are soluble in water, but then again these gases, carbon dioxide, ammonia, HCl, they are highly soluble in water. So that is what is the first factor on which the solubility of the gas depends. Now the second factor on which the solubility of the gas depends is nature of solvent. So that's why this we could have discussed it as a single point, nature of the gas and the nature of the solvent, but let's make it into 2. Now the solubility of the gas also depends on different kind of solvent. Now if you are talking about gases like nitrogen, oxygen, or you can also discuss about carbon dioxide. Yeah, if you are talking about these gases, yeah, just now we discussed already of the nature. You can see nitrogen there on the top, oxygen also on the top, but carbon dioxide is on the bottom with respect to water, but still I am grouping them together. These gases are more soluble in, they are soluble more in ethyl alcohol. So that means the solubility of these gases are more in ethyl alcohol than in water. So that means not only it depends on the nature of the gases, what kind of gases they are, but it also depends on the it also depends on the solvent that you are taking. So that means what liquid you are taking. So if you are comparing to ethyl alcohol and water, if this is ethyl alcohol and the water, these gases are more soluble in ethyl alcohol than in water. That means more quantity of volume of these gases can dissolve here as compared to that of water. That means we can say the second factor, solubility of the gas, can also depend on the nature of the solvent. the nature of the liquid or nature of that particular substance that you are taking to dissolve the gas. So that is what is your second factor. Now the third factor is temperature. Okay, generally speaking, now if I am talking about one solvent, that is water, the most common. Let's suppose here in this water, carbon dioxide is dissolved or oxygen is dissolved or any gas, it can be HCl, ammonia, any gas. Let's suppose we have dissolved the gas. Certain quantity of carbon dioxide is already dissolved in this under normal condition. Then it has been noticed that with the rise in temperature, if the temperature of the gas, if the temperature of the solution is increased, so increase in temperature, I have made arrow up means temperature increase. Increase in temperature is giving, you will see most of the carbon dioxide, as you keep on heating this, gases starts escaping, gases starts going out. That means with the increase in temperature, solubility of the gas, I am talking here about a gas, alright, not see, since we are discussing about solubility of the gas, not of liquid or not of solid. So solubility of the gas in a liquid decreases with the increase in temperature. So if temperature is increased, if temperature increases, solubility of the gas decreases. That means I can now use the word inversely proportional. So here with the increase in temperature, solubility, that means more the temperature, more gases will escape. So escape means the very little quantity of gas will be left. So less quantity of gas left means solubility is less. So generally speaking, the solubility of the gas decreases with the increase in temperature. But it has also been seen that gases like hydrogen and inert gases. Now I don't have to tell you what inert gases are. So many inert gases are there. Any inert gases, you can talk about helium or a neon or a krypton, xenon, whatever gases. Hydrogen and inert gases, it has been seen that the solubility of these gases increases slightly, not too much, but increases slightly with the increase in temperature. See, just the opposite of what you saw here. That means if the temperature increases here for these two gases, not two, in fact here inert gases many, hydrogen and inert gases, with the increase in temperature, it has been seen that these two gases or this kind of gases, inert gases and hydrogen, their solubility increases. So that means here I can use the word directly proportional. Now generally if you ask, then how does temperature affect the solubility of the gas? Then I'll say generally for almost all gases, solubility and temperature, they are inversely proportional. But gases like hydrogen and inert gases, the solubility and temperature, they are directly proportional. This is what is your third factor. Now going on to the fourth factor, now that is what we have to discuss in detail, because fourth factor is pressure. Now when you go to pressure, then our Henry's laws will come into effect now here. I think a very very important part of your chapter, Henry's law. Then after that I think we'll follow it by Raoult's law. Now since our fourth factor is the pressure, so let me now rub the board and move on to that Henry's laws, or the fourth factor, which is your pressure. Okay, then the fourth factor is pressure. Now the relationship between pressure and the solubility of gas was very nicely coined or given by a person or the chemist named Henry in 1803. So this actually law came into being in 1803, so that's why, since it was coined by Henry, so that's why it's called Henry's law. So we'll discuss what that Henry's law is. Now that will actually explain to you the fourth factor, which is pressure. Alright, let me define now what is Henry's law. Again I repeat, Henry's laws will give you the relationship between pressure and solubility of the gas. So since the law is about the gas which is dissolved in a liquid, so that's why the laws go something like this. For a gas dissolved in a liquid or dissolved in a solvent at constant temperature. Now that third factor which we had discussed already about temperature, that must be constant. So for a constant temperature, we say that the concentration of the gas dissolved in the solvent is directly proportional to pressure. That means we can now say that concentration of the gas And you know what is the meaning of concentration? Greater the amount of gas, more is the concentration. Greater the mass, greater is the concentration. So greater the concentration, or we can say concentration of the gas which is dissolving in a liquid or in a solvent is directly proportional. And you know what is the meaning of that. Directly proportional means when the temperature, when the concentration, when the pressure is increased, the concentration of the gas also increase. That means with the greater the pressure, more will be the concentration of the gas. And don't forget, when I say more the concentration means more will be the solubility. So then solvent is directly proportional to what? Proportional to the pressure. So that means greater the pressure applied to the liquid, to the solution, so more will be the solubility. That is what is the meaning. That is why you know that your Henry's law can be actually stated in 5 different ways, many different ways. Like here we discuss about concentration. Since concentration depends on the mass, if you like, then this concentration can be changed into mass. You can say that for a gas which is soluble in a liquid at constant temperature, instead of saying concentration, now you can say the mass of the gas dissolved in the liquid or dissolved in the solvent is directly proportional to the pressure of the gas. That is one way of saying it. The other way of saying it is by with also respect to partial pressure. You can also say, instead of saying all these concentration also, you can simply say solubility. Now let me say the other way of this one, Henry's law. Henry's law states that for a gas which is soluble in a liquid or in a solvent at constant temperature, now instead of saying concentration of gas, I'll say the solubility of the gas in the solvent is directly proportional to the pressure. Now this is what is your Henry's law. As I said, it can be stated in different ways. Many different ways are there in which you can state this one. Now I'm coming on to the last, the most important one, where there is a mole fraction, because that may help us in some numericals, so that I'm coming to that. But first let's see this one. It says that concentration, here it is then. If we are talking about concentration of the gas, if C is the concentration of the gas, is directly proportional to the pressure, is concentration of the, let me write small p as the pressure of the gas, P gas. Now if I want to remove this proportional sign and convert this into an equal to sign, then you know concentration of the gas is equal to, now when a proportional sign is changed into a equal to sign, then I have to add a constant, and the constant is KHG. This is what is for a gas, and this KH here stands for a constant, and this constant is what is called into pressure of the gas. So this same pressure of the gas is what I have written, but only thing is that proportional sign, when changed into an equal to sign, I have to add a constant, and this proportionality here is what is called Henry's law constant. So this KH that you see here is what is your Henry's law constant. Now again, instead of saying concentration, now see, I said the other way of saying it. If you had replaced this concentration with mass, then this I can write M, mass of the gas. Same thing is what is applicable here also. Or solubility, if I want, then I can also write solubility of the gas, same. So as I said, 5 different ways of stating this law. Now let me go to one statement which is with respect to your mole fraction. So then let's see what exactly that states or says. Then from there, and I hope you have not forgotten what is mole fraction. In my first class of solution, I have discussed about what is mole fraction. Mole fraction represented by symbol X. For example, if you are talking about mole fraction of a gas in a liquid, for example, if ammonia gas has dissolved in water and ammonia gas, then how much of quantity of ammonia and how much quantity of water has been taken to dissolve that ammonia in water? You know that we have to do, if I want to find ammonia mole fraction, then here if I want to find mole fraction of ammonia, then I need number of moles of ammonia over number of moles of ammonia plus number of moles of water. So, and you know how to find number of moles. Number of moles is calculated by dividing the mass of the gas which has dissolved divided by its molecular mass, or weight of the gas divided by its molecular mass. So how much, for example, if they say 17 gram, or if they say here 18 gram, or if they say 36 gram, whatever they say, whatever mass is given, that mass when you divide by the respective molecular mass will what is going to give you the number of moles. This is how actually we calculate the mole fraction. So then I am going on to that part of your definition of your Henry's laws where mole fraction is mentioned. Okay, then let's see what is that. So it states that the partial pressure of a gas in the vapor phase, so gases in the vapor phase, is directly proportional to the mole fraction of the gas over the solution. Again, I am repeating what it says. It says about partial pressure of the gas in the vapor phase. Partial pressure of the gas in the vapor phase is directly proportional to the mole fraction of the gas over the solution. That means if that is represented, statement, okay, I am not writing this statement, I hope I have said 2 or 3 times, so I think you have understood what I mean. Now then here you are, the partial pressure of the gas, if I am writing this as partial pressure P, is directly proportional to the mole fraction of the gas. Now again, if I want to convert this proportional sign into equal to sign, then here partial pressure of the gas is equal to, again here I am going to write that Henry's law, constant gas into mole fraction of the gas. Now in case if you have forgotten how to calculate the mole fraction, now then again further, if I am replacing that, this is kH of the gas, then just now I wrote how to calculate the mole fraction of the gas. Mole fraction of the gas is calculated as number of moles of the gas over number of moles of the gas plus number of moles of solvent. So solvent means that liquid which you are taking. So yeah, this is what is the formula for calculating the number of moles of the gas. So number of moles, mole fraction of the gas. Mole fraction of gas is calculated as number of moles of the gas over the total number of moles of both the solute and the solvent. Since our solute is the gas and our solvent is the liquid, water, whatever it is. So this is how you calculate. So at some places now you may come across, for your numericals, you may come across this expression. Now this is what is your 4 factors on which the solubility of gas in a liquid depends. Now how do we explain the solubility of a gas in a liquid with respect to increased pressure? Now I am still on to the 4th factor, so that is going further with respect to Henry's law. Henry's law says that if you increase the pressure, then solubility of gas also will increase. But then again, why? Now in chemical equilibrium, you know that there is something which is called Le-Chatelier's principles. In that Le-Chatelier's principle, it states that whenever any gas, not only gas, any chemical is under stress, maybe there is a stress of pressure, maybe stress of temperature, maybe certain physical condition change. Whenever it is under the stress, it always tries to shift its equilibrium, means it will try to go towards that side, right side of the equation or left side of the equation. It will try to shift its equilibrium to that side which will annul the stress. Annul means which will cancel the stress, or it will try to reduce the stress as much as possible. Now let's imagine then, now how can we explain Henry's law with respect to your Le-Chatelier's principle? Now think that here we have the liquid, and in this liquid some gases have already dissolved, and some gases are, let's suppose, here inside, some gases are here inside which has not dissolved, because that is what is the solubility of gas. Now this extra gases cannot dissolve because it is under normal pressure. Now see what happens. You increase the pressure now. Let's suppose you have you will pull down this piston. Let's suppose now the piston you are bringing it down here. Now the same amount of gas, now they are getting very little space now. Now the pressure is increased. Now if the pressure is increased, now the gas is under tremendous stress. Tremendous pressure is what is being built up here. Now to annul that stress, to cancel that stress, to minimize that stress, now some gases here now will start dissolving in a liquid, because they want to cancel out the stress. So much of stress is here in this area. So to cancel out that stress, according to Le-Chatelier's principle, now some amount of gases will start dissolving here. So then dissolving means now solubility has increased, now more gases has dissolved. So that is why with the increase in pressure, solubility of the gas is increasing. This is how we can explain. Now if you ask for a reason about why increase in pressure, or what is actually Henry's law trying to say, then you can say it in terms of this Le-Chatelier's principle. With the increase in pressure, more gases will be soluble, so that means the solubility of the gas is what will increase. Now our next topic is, since we are here still on to the fourth factor, Henry's law. Now what are the applications of Henry's law? Now there are many applications, like in our day-to-day life. Now we may come across many application of this, the increase in pressure, solubility. Now one such thing that we can discuss about is about solubility of a gas in a liquid. Now think about your cold drinks or maybe your soda water. Now your soda water is actually nothing but a carbon dioxide which is dissolved in water. Now if under normal pressure, if carbon dioxide is dissolved in water, very little amount of carbon dioxide only will dissolve. But when carbon dioxide is dissolved in water under high pressure, now you are pressurizing this carbon dioxide. So when you apply the pressure, more carbon dioxide will dissolve. So that's why when you are opening a soda bottle, you are releasing the pressure, and that is why carbon dioxide is what is coming out along with the soda. So that is what is one application you can say of your Henry's law. Then another application that we can talk about is a situation which usually arises when with the sea divers. They suppose, for example, you know that you have heard about scuba diving. Now they go very deep down in the sea. When they go deep down in the sea, you know, they carry with them the oxygen cylinder, but then you know that air cylinder if they carry, then usually what happens when they go deep down, very deep down inside the sea, you know, pressure increases. And if pressure increases, what happens is not only your oxygen will be going inside through the lung, but then you know nitrogen also goes inside and dissolves in the blood. So here not only oxygen, yes, oxygen is supposed to go to the blood, but not only oxygen, because oxygen solubility is already high, but then because of very high pressure, because you are pressurizing, so under very high pressure even nitrogen starts dissolving in the blood. And then when the scuba diver is actually coming up, you know that because of the decrease in pressure, now as he is coming gradually up, because of the decrease in pressure, that dissolved nitrogen is what is released into the capillaries which actually supplies blood, which carries blood. Now when nitrogen is released in the blood vessel, you know, when nitrogen is released, now you know bubbles of nitrogen is what is released, and that can cause a very severe pain. Okay, so that condition is actually called bends. Now it's very painful. Now if it is very painful, then how do we actually remove this? That's why it is rather than taking the air, instead of taking air inside the cylinder, the scuba diver, now it is advised that along with oxygen it is mixed with helium. So when helium is mixed, so that production of gas, releasing of the gas into the blood vessel or into the capillaries is what is prevented. So that way now what we can do is, now see all this what we are discussing is application of Henry's law, and because of this Henry's law, which actually says that solubility increases because of pressure. As you go down deep down in an oxygen cylinder, if you have along with oxygen, if nitrogen is also there, it causes a problem. So that's why now we no longer use nitrogen. So along with oxygen we use inert gases like helium. So that when it is then that very bend, the situation which is there, which is the name, very severe pain is what, and that usually causes bending of that particular person. Because of that only, you know, the name bend is what is being derived. That is what is your second application of your Henry's law. Now going on to the third one, then you already know that this also like climbers. Now when they are climbing the mountains, you know, as they go up, their oxygen supply, you know that pressure decreases, and because of which the supply of oxygen into the blood is what is very less. So that means you are now supplying to your lungs a very less amount of oxygen. Now as you are supplying very less amount of oxygen, so that may cause a weakness. And yes, why? Because of the fact that as you are going up, pressure is decreasing, solubility of oxygen into the blood is what is will be less. So that means the blood, when I am talking about the blood, you know, the hemoglobin which will be carrying oxygen. So that since oxygen itself is not dissolving properly at very high altitude because of less pressure, so because of which oxygen supply to different part of the body is what is hindered. That very supply is what is not sufficient, and that causes weakness. That not only causes a weakness, it also causes a very I would call it as acute sense of thinking, let's call it as clarity of thinking. You cannot think it properly, clearly. So that means it appears as if then maybe you are talking about all nonsense, you are not able to think properly. So almost you will be acting like a madman. So this is what, so that this very, sickness is what is called anoxia. We call as a, like how we have bend here in deep sea diving. Same kind of condition is the clarity of thinking will be gone. Weaknesses is what you will be feeling. And this very sickness is what is called anoxia. So this is also because of this only. With the increase in pressure, solubility of the gas is what is decreased. So these are some of the, you can call it as application. Also other applications are there, you can go through this one. But then again, these are three main applications of your Henry's law. Now finally, with respect to Henry's law, I think the last topic that you have is limitation. Limitation means defects. What are the defects of Henry's law? Now, Henry's law is applicable. The first defect I can say is that Henry's law is applicable only for ideal gases. Now, if you talk about what are ideal gases are those gases which obey Rawls' law. Now, don't ask me what is Rawls' law, because our next topic is Rawls' law. So, those gases which obey Rawls' law are ideal gases. And those who don't, they are non-ideal gases, or we call them as real gases. So only applicable for ideal gases, not applicable for real gases. That is why, that is what we can call it as one limitation. And Henry's law is not applicable for those gases, like we are dissolving a gas in a liquid. It's not applicable for those gases which undergoes chemical reaction. For example, if one particular gas, if I want to take, for example, ammonia gas, I want to dissolve in water, but instead of dissolving, ammonia gas is highly soluble in water. But not only will it be soluble, ammonia gas also starts reacting with water to form ammonium hydroxide. So if it reacts, so if it is reacting instead of physical change, because solubility is a physical change, whether a gas is soluble or not soluble, it's a physical change. But then when a reaction between the two starts, then you know your Henry's law will not work. So that means it is also not applicable for those gases which start chemical reaction with the solvent. So that is not applicable. Then also third one, Henry's law is not applicable for those gases which undergoes dissociation or ionization. Okay, now I think this example I can give you, like HCl when dissolved in water. If it simply dissolves, then it was fine. But you know, HCl when dissolved in water, it undergoes a chemical dissociation like this, ionization. Ions are formed, and when ions are formed also, so this kind of dissociation, ionization, when it is also taking place, when a gas is put into a liquid, so even you know that Henry's law is not applicable for such. So this is what is here things which are related with Henry's law.
Gases dissolve in liquids to form solutions. Generally, gases that are easily liquefiable are more soluble in a solvent. For example, carbon dioxide is more soluble in water than oxygen at a given temperature. Oxygen dissolves in water to a very small extent, about 5 to 10 milliliters per liter of water. However, even this small quantity can sustain aquatic life. The dissolution of gases in liquids is an equilibrium process. At equilibrium, the rate at which the gaseous solute molecules escape the solution equals the rate at which the molecules re-enter the solution. An increase in pressure results in more molecules of the gas striking the surface of the liquid and entering the solution in a given time. Therefore, at high pressure, more gas dissolves in a given volume of liquid than at lower pressures. This proportionality of the solubility of a gas to pressure was first proposed in 1800 by William Henry and is known as Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas. Dalton, a contemporary of Henry during the same period, concluded independently that the solubility of a gas is a function of its partial pressure. If the solubility of a gas is expressed in terms of the mole fraction, then the statement of Henry's law becomes: the mole fraction of a gas in a solution is proportional to the partial pressure of the gas over the solution. However, the most commonly used version of Henry's law is: the partial pressure of a gas in vapor phase, P, is proportional to the mole fraction of the gas, X, in a solution. Mathematically, it can be represented as P is proportional to X, or P is equal to KHX, where KH is the Henry's law constant. Further, if you plot a graph between P, the partial pressure of a gas in vapor phase, and X, the mole fraction of the gas in a solution, then you will get a straight line passing through the origin with its slope equal to KH. The graph also shows that as P increases, X, the mole fraction of the gas in a solution, also increases. The Henry's law constant, KH, for some common gases in water as the solvent are given in the table here. On comparing the values of Henry's constant for oxygen and nitrogen, we can infer that the value of KH increases with an increase in temperature. As a consequence, the solubility of gases generally decreases with an increase in temperature. Also, if the dissolution of gases in liquids is considered as a process similar to condensation, then it is an exothermic process, where a dynamic equilibrium is established between the gas and the solution phase. On applying Le Chatelier's principle to this equilibrium, we see that the solubility of a gas decreases with an increase in temperature. It is seen that when water is heated, bubbles of gas appear on the sides of the container well below its boiling point. These are bubbles of air, which are evolved when water, which is air saturated at lower temperatures, is heated. It is interesting to note that hot water tastes flat because the oxygen in it has been expelled by heating. Have you ever wondered why aquatic species are more comfortable in cold water rather than in warm water? This is because the solubility of oxygen is more at low temperatures. Let us now discuss some important applications of Henry's law in the industry as well as in biological solutions. Carbonated drinks are packed under high pressure of carbon dioxide, some of which gets dissolved in the beverage. When the bottle is opened, the partial pressure of carbon dioxide above the solution drops. As a result, some of the dissolved carbon dioxide comes out of the solution as bubbles. Henry Murray's law has an important application for scuba divers. The pressure is very high deep in the sea. As a result, the amount of nitrogen dissolved in the blood and other tissues of deep sea increases. If the diver returns to the surface too rapidly, then the nitrogen forms bubbles in the blood as it becomes less soluble due to a decrease in the pressure. These bubbles are dangerous as they can plug small arteries and cause serious damage by stopping the flow of blood to a particular organ. Divers may experience this potentially painful and lethal condition called the bends if they do not ascend to the surface slowly, allowing themselves time to adjust to the lower pressure at the surface. To alleviate this problem, artificial breathing mixtures consisting of 32.1% oxygen, 56.2% nitrogen, and 11.7% helium are used. Helium is 5 times less soluble in blood than nitrogen. As a result, there is less dissolved gas to form bubbles. On the other hand, at high altitudes, the atmospheric pressure is low and there will be less concentration of dissolved oxygen in blood and tissues. Therefore, mountaineers at very high altitudes suffer from anoxia, which is low oxygen supply in the tissues, accompanied by weakness and inability to think clearly. That is why mountaineers carry oxygen cylinders at high altitude.